The law of sines is one of the cleanest ways to handle triangles that are not right-angled. Its real strength is that it connects sides and opposite angles in a proportional way, so you are no longer trapped inside a Pythagoras-only mindset. In CAT, that matters because many problems hide a usable ratio pattern rather than asking for brute force computation. Once you start seeing triangles as proportional structures, the topic becomes much easier to control. The logic behind the law of sines is straightforward once you slow down and read the structure. First, identify the opposite side angle pair. Then extract the sine value for the angle you know. After that, log the proportional ratio across all corresponding side angle pairs. The most important habit here is to look for the linked pair first, because that is what unlocks the whole triangle. This formula works because triangle areas and side lengths create consistent ratios, so the geometry never loses its balance. Larger angles naturally face wider opposite sides, which is why proportionality appears so cleanly here. The deeper idea is that equating area expressions leads to stable mathematical ratios, and that gives the law of sines its power. In other words, this is not just a formula to memorize, it is a structural relationship to recognize. The golden formula is A over sine A equals B over sine B equals C over sine C. That means each side is tied directly to the sine of its opposite angle. The rule only works when you already know at least one side angle pair. So the first step is always to identify what is fixed in the triangle. A smart exam habit is to think in ratios, not in isolated numbers, because the whole formula is built on proportional comparison. This challenge problem is a classic triangle setup in disguise. A ship navigation style context is really asking you to track a triangle through angles and a known side, and then use the sine rule to extract the target distance. The key is to ignore the story noise and focus on the paired ratio. Once the angle-side relationship is spotted correctly, the problem becomes much simpler than it first appears. The standard solution follows the direct ratio method. With sine 30 degrees equals 0.5 and sine 45 degrees equals 1 over root 2, you plug into the law of sines and solve for the required side. The answer comes out exactly by manual simplification, which is neat, but still a little time-consuming if you do it the long way every time. The main lesson is that the formula gives the result cleanly, but speed still depends on how quickly you notice the pattern. The topper's approach is much faster because it avoids unnecessary decimal work. Instead of converting everything into cumbersome numbers, you keep the ratio in sine form and compare directly. That gives the compact mapping 1 over 2 to 1 over root 2, which simplifies to 1 to root 2, and the target distance drops out very quickly. This is exactly the kind of mental math shortcut CAT rewards. Preserve structure, simplify only at the end, and save time without losing accuracy. The tricky part of the sine rule appears in the ambiguous SSA case. When you know two sides and a non-included angle, the triangle may not be unique, so the geometry can produce 0, 1, or 2 solutions. That is why you must check the supplementary angle as well, instead of blindly accepting the first inverse sine result. This is a common trap because the calculator gives an answer, but the triangle may still allow another valid configuration. Speed here comes from refusing to overconvert. If you start turning everything into decimals too early, you lose the elegant ratio structure that makes the sine rule fast. The direct shortcut is to work with raw trigonometric fractions and preserve the proportional logic until the end. A good takeaway is that special angle values often do the real work for you. So the strongest solver is usually the one who keeps the math clean, not the one who makes it long. The advanced formula on this slide is really about handling the ambiguous case carefully. Since sine of theta equals sine of 180 degrees minus theta, A single sine value can correspond to two possible angles. That is why the reverse check is so useful. One possible angle is sine inverse of x, and the other is 180 degrees minus sine inverse of x. Memorizing this saves you from missing dual triangle configurations, which is exactly where many students lose marks. The cheat sheet brings the full topic into one compact revision frame. The core formula is sine A over A equals sine B over B equals sine C over C. The rule applies cleanly to AAS, ASA, and SSA cases. And the shortcut is to think in side angle proportions rather than isolated values. The real insight is that SSA can yield 0, 1, or 2 possible triangles. So the answer is not always unique. If you keep that structure in mind, the law of sines becomes a reliable scoring tool instead of a formula to fear. Law of cosines is one of those tools that turns a messy triangle into a manageable one. The real idea is simple. When a triangle is not right-angled, you still do not lose control of it. You just switch to a more powerful framework. That is why this formula matters so much in CAT. It connects sides and angles in a way that often beats pure Pythagoras. The best habit here is to stop seeing it as a formula and start seeing it as a shortcut for non-right triangles. The logic is beautifully clean once you see the structure. You begin with two sides and the included angle, and the formula gives you the opposite side exactly. In spirit, it is Pythagoras with an angle correction factor, which means it works even when the triangle is not right-angled. That's the main exam advantage. It identifies the missing link instantly and avoids forcing a right triangle mindset where it does not belong. The reason this formula is so valuable is that it fills the gap in cases where ordinary right triangle methods fail. It handles acute triangles, obtuse triangles, and vector resultant type problems with equal ease. That makes it a generalization of Pythagoras rather than a separate topic. In CAT, this matters because the test often hides geometry inside a practical setting, and this formula is one of the fastest ways to extract the answer. The golden formula is the one you should lock in without hesitation. C squared equals A squared plus B squared minus 2AB cosine of C. Here C is the unknown side opposite the angle, A and B are the adjacent sides, and C is the included angle between them. The real conceptual point is that cosine adjusts the geometric contribution of the two sides. When the angle is 90 degrees, cosine becomes 0 and the formula collapses neatly into standard Pythagoras. That is the perfect check to keep in memory. This is a hybrid setup where geometry meets time and speed. You're given two sides, 50 kilometers and 70 kilometers, with an included angle of 60 degrees, and the third side C represents the gap to be covered. So the first instinct should be geometric. This is the triangle problem before it's a speed problem. Once you visualized a triangle clearly, C becomes the third side opposite the 60-degree angle, and only after finding that distance do you bring in the speed of 10 kilometers per hour to get the time. The key here is sequencing. Don't jump to speed too early. First fix the geometry, then move to time. The standard solution follows the clean geometric path. First, substitute directly into the law of cosines using the given values. Then simplify to get C squared equals 3900, which gives C approximately 62.45 kilometers. After that, divide by the speed to get the time, which comes to about 6.24 hours. The solution is correct and structured, but it is also the kind of process that can feel a little slow under pressure, which is exactly why shortcuts matter. The topper's approach saves a huge amount of time by using mental scaling. If everything can be scaled down by 10, then the sides become 5 and 7, and the angle remains 60 degrees. That makes the computation much lighter. C squared equals 25 plus 49 minus 35, so the side is 10 root 39, which scales back to about 62.4 kilometers. The big lesson is that mental math wins when the structure is simple enough to compress. You do not need to write everything when the ratio logic is already doing the heavy lifting. This slide gives one of the most important conceptual cues in cosine geometry. Cosine tells you the triangle type. Positive cosine means an acute angle, while negative cosine means an obtuse angle. That means the sign is not just a number, it is information about the shape itself. The common mistake is forgetting that obtuse angles bring in a negative cosine, which changes the algebra in a very specific way. If you remember that, you avoid one of the easiest traps in the topic. Special angles create the best speed hacks, and 120 degrees is a perfect example. Since cosine of 120 degrees equals negative 0.5, the formula simplifies immediately to c squared equals a squared plus b squared plus ab. That is a beautiful shortcut because it removes the need to recalculate from scratch every time this angle appears. In CAT, such angle patterns are often there precisely to reward quick recognition rather than long derivation. The reverse form of the law of cosines is equally useful, especially when the angle is unknown. If you know all three sides, you can isolate the cosine and solve for the angle directly. The structure is simple. Add the adjacent squares, subtract the opposite square, then divide by 2ab. This is the SSS case in action, and it is a powerful tool for unlocking unknown angles quickly. Once you know this reverse form, the formula becomes a two-way street instead of a one-way trick. The cheat sheet ties the whole chapter together in one compact memory block. The core formula is c squared equals a squared plus b squared minus 2ab cosine of c. The rule is SAS for sides and SSS for angles. The shortcuts include ratio scaling and the 120 degrees algebraic hack. And the observation is that this is really a perfect generalization of Pythagoras. That is the full mindset you want in CAT. Use the framework, respect the structure, and let the formula do the work. With that, this topic becomes one of the most reliable scoring areas in geometry. Trigonometric equations and identities are really about pattern recognition dressed up as algebra. The moment you stop seeing them as random formulas and start seeing them as repeating structures on the unit circle, the topic becomes much easier to handle. This opening slide already sets the right mindset. The goal is not rote memory, but fast visual reasoning. If you can connect the graph, the angle, and the identity in one mental picture, you're already ahead. A trig equation is basically a repeating wave trying to tell you its valid angle values. The base angle goes into the function returns a ratio value, and periodicity creates infinitely many valid answers. That is why one solution is never enough in this chapter. The exam insight here is very important. Solutions repeat every 2 pi or every pi depending on the function. So you must always think in cycles, not just single values. The real value of identities is that they save time and reveal structure. They simplify long expressions instantly, uncover hidden quadratic forms, and help you get exact values without ugly decimal work. That is why identities are so powerful in competitive exams. They do not just solve problems, they reduce them. The strongest students are usually the ones who spot the right identity early and avoid unnecessary expansion. The identity sine squared theta plus cosine squared theta equals 1 is the backbone of the whole subject. On the unit circle, sine is the vertical projection and cosine is the horizontal projection, and together they always satisfy this fixed relationship. That is why cosine squared can immediately be rewritten as 1 minus sine squared theta, or vice versa. A lot of advanced simplifications begin with this one bridge, so it is worth understanding it geometrically rather than treating it as a formula to memorize. This challenge problem is a clean test of whether you understand quadrant-based trig values. You are given cosine theta equals 5/13 in the first quadrant and asked for the exact value of sine of 2 theta. The quadrant condition matters because it guarantees a positive sine value. The real skill here is not just solving the problem, but recognizing that the ratio 5/13 immediately suggests a 5-12-13 triangle, which makes the rest much easier. The standard solution follows the safe route. First, find sine theta using the Pythagorean identity. Then, apply the double angle formula sine 2 theta equals 2 sine theta cosine theta. That gives the exact answer. It is a reliable process, and beginners should definitely know it well. At the same time, the slide's exam warning is correct. This method is accurate, but it can be slower than it needs to be in a timed setting. The topper's approach is all about immediate recognition. If cosine theta equals 5/13, the triangle must be the familiar 5-12-13 triplet. So sine theta is instantly 12/13. Once that clicks, the double angle result follows almost automatically. This is exactly the kind of mental shortcut that saves time in CAT-style problems. The important habit is to train your eye to recognize triplets before you start calculating. Quadrant signs are one of the most common places where students lose marks. The slide makes the trap very clear. If you ignore the quadrant, you may get the magnitude right, but the final sign wrong. The ASTC rule is the simplest way to stay safe. All in Q1, sine in Q2, tangent in Q3, cosine in Q4. Another strong strategy is to sketch the right triangle or reference angle first, because that keeps the sine logic grounded. The speed hat shows how much faster things become when you memorize the standard angle combinations. For 75 degrees, you do not need to expand everything every time if you already know the exact value. The slow method works, but the fast method wins in exams because it removes unnecessary algebra. The takeaway is practical and clear. Pre-learn the high-frequency angles so you can answer instantly instead of rebuilding the result each time. The double angle identity for cosine is one of the most useful advanced tools in the chapter. You can write it as cosine of 2 theta equals cosine squared theta minus sine squared theta, or convert it into the form 2 cosine squared theta minus 1 or 1 minus 2 sine squared theta, depending on what simplifies the problem best. That flexibility is the real strength of identities. They let you choose the most efficient representation for the situation in front of you. This cheat sheet is the perfect endpoint for revision. The core identity, quadrant rules, triplet shortcuts, and double angle/half angle ideas all sit together here as one toolkit. The final message is the one to remember most. Stop calculating everything from scratch and start seeing the patterns. When the unit circle becomes familiar, trigonometric equations and identities stop feeling like a memory chapter and start feeling like a logic chapter.